Okay, in this video we're going to be looking at how to deal with hypothesis testing and confidence intervals with two proportions. In the past we looked at hypothesis testing with only one sample statistics. Here we're going to be looking at two sample statistics here when we're dealing with two proportions here. So we'll be looking at how to test a claim about two population proportions, and also we'll be constructing confidence interval estimates of the difference between the two population proportions. Alright, to begin with, we need to start off with a little bit of notation that's going to be used in this particular section. So here, this will be notation. And we're going to be looking at notation that deals with the first population, because we're testing two proportions, so we have to have two populations here. One will be population 1 and the other one will be population 2. Okay, in this case here, if we're dealing with a population proportion, which is what this section is all about, then the notation for population 1 would be P sub 1. That would be the first population, and then P sub 2 represents the second population proportion. So P1 is the first population proportion, P2 is the second population proportion. And then you have your sample size coming from that population. And usually n is going to be the sample size. So from the first population, your sample size will be represented by n1 or n sub 1. And then for the second population, your sample size will be represented by n sub 2. And then you have your number of successes. And usually that's represented by the variable x. X represents the number of successes. So from the first population, your number of successes will be represented by x sub 1. And from the second population, the number of successes will be x sub 2. And then you have your sample population. Sample proportion. Usually the sample proportion is always going to be the number of successes, which is your x, divided by the sample size, which is n. So in this case here, we use p hat for the sample proportion. So for the sample proportion from the first population, that will be p sub 1 hat, or p hat sub 1. And that's going to be equal to x1 divided by n1. And then for the second population, your sample proportion will be represented by P sub 2 hat, which will be equivalent to x2 divided by n2. Okay. And then finally we have the complement. Because once you know what P is, you can always find out what Q is, which is always going to be 1 minus P. So for the first population, Q hat sub 1 would be 1 minus P hat sub 1. And then for the second population, Q2 hat would be, or Q hat sub 2 would be 1 minus P hat sub 2. So that's pretty much the notation that we use in this particular section when we're dealing with two proportions. Okay. Now, when we do a hypothesis test or even a confidence interval, we do have a couple of requirements that we have to meet in order to do a hypothesis test or a confidence interval. So here, these are the two requirements. The first one, the sample proportions are from two samples that are independent. Okay, so we'll say sample proportions are from two samples, or two simple random samples that are independent. And what do we mean by independent? That means that the sample values selected from one population are in no relationship or somehow naturally paired or matched with sample values that are selected from the other population. So the first sample has no relationship with the second sample. And then second, for each sample, the number of successes is at least 5. Successes is at least 5. And the number of failures is also at least 5. So notation here, if you have n, which is the sample size, times p, which is the probability of success, that product has to be at least 5, meaning greater than or equal to 5, and n times q, that's the probability of getting a failure, that product must be greater than or equal to 5 as well. Okay, so those are the two requirements for a confidence interval and also for a hypothesis test. And once those requirements are met, we can do either the hypothesis test or the confidence interval. Now, let's look at the test statistic for a hypothesis test. So here the test statistic for two proportions, and that is where your null hypothesis, which is h sub 0, is set as this: p1 is equal to p2. The first proportion is equal to the second proportion. And that test statistic is this. It's going to be a z-test. So we're going to be using z is equal to p1 hat minus p2 hat minus p1 minus p2, and that's all divided by the square root of p bar times q bar divided by n1 plus p bar times q bar divided by n2. Now this test statistic formula is used where p1 minus p2 is equal to 0. And that's basically assumed in the null hypothesis because p1 is equal to p2, so if you subtract p1 minus p2, that difference will be 0. Okay. Now let's explain what some of these variables represent. P1, as I've already mentioned, is of course x1 divided by n1, and P2 hat, or P1 hat is x1 divided by n1, P2 hat would be x2 divided by n2. Those are your sample proportions. But this P bar that you see in the denominator here, that's going to be equivalent to x1 plus x2 divided by n1 plus n2. We call this the pooled sample proportion. What this means is that you're pooling all of your resources for N1 and N2 and your number of successes as well. So that's why we call it the pooled sample proportion. Okay, and once you find out what P bar is, that Q bar is just its complement. Q bar would just be 1 minus P bar. So that's going to be the test statistic for your two proportions. Now, to find the p-value, we're going to be using table A-2. And table A-2 is actually the standard normal distribution table. Now the standard normal distribution table looks like this. This is just for negative z-scores here. And of course, if you recall from the other videos, that standard normal distribution is only used for the cumulative area from the left. Okay? And that's for negative. This one is for positive z-scores. Because we're doing a z-test statistic, so we have to use the normal distribution table in this case. Okay, now for the critical value, or critical values, I'm going to use what they call the common critical z-value table for hypothesis testing. And this is what that table looks like. Okay. So here, if you have a one-tail test, you'll find the appropriate level of significance in that first column, and then read across to find out what that critical value is. Or if you have a two-tail test, then you look in the middle column to find the level of significance, and then find your critical value in that particular column. Okay, so that's the common critical z-values here that we'll be using. Or the best way to do this will probably be using technology, and I'll show you how to use the TI-83 or 84 Plus calculator to do this. Okay, and also we have a confidence interval for two proportions as well. So we'll discuss that. So I'll go ahead and give this to you, the confidence interval. Estimate. And that's for P1 minus P2. Confidence interval. estimate for P1 minus P2. Now that confidence interval for two proportions will be this: P1 hat minus P2 hat minus E, which is your margin of error, that's less than P1 minus P2, and that's less than P1 hat minus P2 hat plus E. And that's where the margin of error, which is what E is, so your E is going to be the margin of error. That's going to be equal to this: Z of alpha over 2, which is the critical Z value, multiplied by the square root of P1 hat times Q1 hat, all divided by N1, plus P2 hat times Q2 hat, all divided by N2. Okay, now these are separate from each other here, underneath the square root symbol. Okay, so that's going to be the margin of error. Okay, so you first have to find out what P1 hat is going to be and P2 hat is going to be, because those won't be given to you directly, because you might be given the number of successes for each sample and the sample size for each sample. Okay, so you have to do X divided by N for P1 hat and P2 hat. And then your margin of error, you'll use this formula here. Once that's done, you'll substitute those values into this interval here. And there is a round off rule, so when you do your confidence interval, you're going to round the confidence interval limits to 3 significant digits, or let's say 3 decimal places. Okay, 3 decimal places is what you round to 3 to round your confidence interval limits to. Okay. And also we can use the TI-83 or the TI-84 plus graphing calculator to come up with the confidence interval as well as the hypothesis testing procedure as well. Okay. Alright, now let's look at some examples of how we can do a hypothesis test and a confidence interval. Okay. So let's look at example E1. And it says in example E1, when games were sampled throughout a season, it was found that the home team won 131 of 171 basketball games, and the home team won 52 of 67 hockey games. The result from testing a claim of equal proportions are shown on the right. And that's this output right here that you see here. Does there appear to be a significant difference between the proportions of home wins? And what do you conclude about the home field advantage? Okay, so here we're going to have to test a claim about two proportions. Okay, because it says that the result from testing a claim that's given to us on the right. So we're going to use that 8-step hypothesis testing procedure to do these types of problems. Now, if you're not familiar with the 8-step hypothesis testing procedure, I suggest you look over the video for section 8-2 for the basics of hypothesis testing, where I introduce that 8-step procedure for hypothesis testing. Okay, so now let's go ahead and start that 8-step procedure. So in this case here, step number 1 is always stating the original claim and writing it in symbolic form. So step number 1 is the original claim. Now in this case here, we want to find out, does there appear to be a significant difference between the two? Okay, so now, significant difference means that the first proportion is not equal to the second proportion. So that means that P1 is not equal to P2. That's your original claim. Step number 2 is the opposite of the original claim. Okay, now the reason why it's not equal to, because it does not give any type of directional language saying whether it's greater than or less than. So significant difference means not equal to in this case. P1 is not equal to P2. Now the opposite would be P1 equals P2, because the opposite of not equal to is simply equal to. So P1 equals P2. And then from steps 1 and 2, we can write our null and the alternative hypothesis. That's step number 3. So the null is the one that has equality in it. And that's this one right here, P1 equals P2. The alternative is the one that does not have equality. That's your original claim. P1 is not equal to P2. So I'm going to write the word claim here. So here, my claim will be the alternative hypothesis. Now, step number 4 is to identify the significance level or your alpha level. In this problem, it's actually not given, but anytime your significance level is not given, we always use the most common significance level, and that will be 0.05. Okay, so here we use 0.05 as the common significance level. Now, step number 5 is calculating the test statistic, which we won't have to do because the output is already given to you right here. So here, up here, your test statistic, which is your Z, that's that negative 0.1652191. But we're going to round this off to 2 decimal places, so that decimal value will be negative 0.17. So here Z is equal to negative 0.17. That's your test statistic. Alright, now step number 6, I'll do this on the right hand side. Step number 6 is finding out what the p-value is. And here I'm using that approach because we're given the p-value right here in this output, which is in this case 0.8687760, but to 3 decimal places I'm going to round that off to 0.869. So 0.869 will be the p-value that's given in that output. So that's step number 6. Now step number 7 is the decision rule. Since we're using a p-value method, we use the decision rule that if your p-value is less than or equal to alpha, you reject the null hypothesis. Otherwise, fail to reject the null. Now looking at this, your p-value is 0.869 from step number 6. .869. And we're going to compare that to our alpha, which we're using the common p-value of the common alpha level of 0.05. As you can see, 0.869 is greater than 0.05. And by looking at this, even though our alpha level or level of significance was not given, if your p-value is high, then the null must fly. That's one of those common rules for p-value. If the p-value is high, the null must fly. But if the p-value is low, the null must go. So here we have a very high p-value here, so the null must fly. So in other words, and besides 0.869 is bigger than 0.05, that means we're going to fail to reject the null hypothesis. So here we fail to reject the null hypothesis. And then step number 8 is the conclusion, written in simple non-technical terms. Here the claim was the alternative. We failed to reject the null. So that means that there is no sufficient evidence that there is a significant difference between the proportion of home wins. And it will help if I move this paper over so you can see. So here there's no sufficient evidence that there is a significant difference between the proportion of home wins. Okay. Now, what can we conclude about the home field advantage? Well, we can conclude that the advantage appears to be about the same for basketball and for hockey. So here we can say here that the advantage appears to be the same or about the same for basketball and hockey. Okay. Since there's no significant difference, so here that home court advantage could be the same. Okay. All right, let's look at another example that has another output. In a randomized controlled trial, insecticide-treated bed nets were treated as a way to reduce malaria. Among 327 infants using bed nets, 21 developed malaria. Among 261 infants not using bed nets, 30 developed malaria. Use a 0.5 significance level to test the claim that the incidence of malaria is lower for infants using bed nets. Do the bed nets appear to be effective? Conduct the hypothesis test by using the results from the given display. So again, we're going to be using an 8-step procedure, and as you can see here, here's the output for that. Now, what I'm going to do here is identify P1 and P2. P1 is going to be the proportion of infants using bed nets. P sub 2 will be the proportion of infants not using bed nets. Okay, so P1 would be the proportion of infants that were using bed nets, and P sub 2 would be the proportion of those infants not using bed nets. Okay, so let's go ahead and start the 8-step procedure for hypothesis testing. Alright, step number 1 is going to be the original claim, written in symbolic form. Okay, in this case here, we're trying to find out that the incidence of malaria is lower for infants using bed nets. Okay, so that means the proportion of infants using bed nets must be lower than the proportion of those infants not using bed nets. So it would be P1 less than P2. Okay. So we want it to be lower for infants using bed nets, so we have to use the less than symbol for the original claim. Now step number 2 is the opposite of the original claim. Well, the opposite of greater than would be, the opposite of less than would be greater than or equal to. So it'd be P1 greater than or equal to P2. That's the opposite of the original claim. Now from that, we can write our null and the alternative hypothesis, which is step number 3. Your alternative always has the statement that doesn't have equality in it. So we have to use the original claim as the alternative hypothesis because it does not have equality in it. So we have to say P1 is less than P2 as our alternative hypothesis, and that's the original claim. The null always has the equal sign, so this will be P1 equal to P2. Step number 4 is stating the level of significance. Now you're told what the level of significance is. That's 0.05, so that's going to be your alpha level, 0.05. Okay. Alright, step number 5 is your test statistic. And that's already given to you in the problem here. The test for the difference, z is equal to negative 2.17. That's your test statistic there. So negative 2.17 is your test statistic. And now step number 6 is the p-value. So they give you the p-value in this particular output. That's going to be 0.015. Okay. Alright, step number 7 is the decision rule. And that's if your p-value is less than or equal to alpha, reject the null hypothesis. Otherwise, you're going to fail to reject the null hypothesis. Your p-value is going to be 0.015. That's given to us. Your alpha level is 0.05. Now, if you compare those two values here, 0.015 is less than 0.05. So that does satisfy the decision rule. So here we can reject the null hypothesis. And then step number 8 is to write our conclusion. And in this case here, there is, now here the claim is the alternative hypothesis. We're rejecting the null, so that means that we are supporting the claim based on the sufficient evidence we have. There is sufficient evidence to support the claim that the incidence of malaria is lower for infants using bed nets. So that's the conclusion statement. Alright, and then they ask, do the bed nets appear to be effective? Well, if there's sufficient evidence supporting the claim that the incidence of malaria is lower for infants using bed nets, then we can say that the bed nets appear to be effective. Okay. So those two examples that I just did had the output already given to you. Okay, now the next three examples that I do, we're going to have to do a little work here. Because here you won't be given the output. Okay, so in this example here, a study was conducted to determine the proportion of people who dream in black and white instead of color. Among 290 people over the age of 55, 60 dream in black and white, and among 306 people under the age of 25, 15 dream in black and white. Use a 0.01 significance level to test the claim that the proportion of people over 55 who dream in black and white is greater than the proportion for those under 25. And you're going to complete parts A through C below. In part A, you're going to test the claim using a hypothesis test. Part B, you're going to test the claim by constructing an appropriate confidence interval. And C, an explanation for the results that those over 55 grew up exposed to media that was displayed in black and white. And can these results be used to verify that explanation? Okay, so now we're going to have to do three parts here. So part A, we're going to do the hypothesis test. Now in this case here, I need to identify some things here. Alright, in this case here, I'm going to let P1 be those people over age 55. And then P2 will be those people under the age of 25. Okay. And now let's start the 8-step procedure here. In step number 1, we need the original claim. Now, our claim is that the proportion of people over 55 who dream in black and white is greater than the proportion for those under 25. So now, P1 greater than P2. Because P1 represents the proportion of people over the age of 55, and that's going to be greater than P2, which is the proportion of people under age 25. Step number 2 is the opposite of the original claim. Well, the opposite of greater than will be less than or equal to. So be P1 is less than or equal to P2. And then from steps 1 and 2, we can write our null and the alternative hypothesis, which is going to be step number 3. So we have to pick which one of these will represent the alternative hypothesis. And that will be this one, because that's exclusively greater than, does not have equality in it. P1 is greater than P2. And that's going to be the claim. The null always has the equal sign, so be P1 equal to P2. Okay. And then step number 4 is your level of significance. And in the problem, you're told to use a 0.01 significance level, so your alpha level is 0.01. Okay. Now, step number 5. Here we're going to have to actually calculate the test statistic. Now, instead of using the formula that I showed you earlier, we can use the TI-83 or the TI-84 plus graphing calculator. Alright, but we need to identify some things like N1, X1, N2, and X2. Let's start off with N1. N1 is going to come from P1, which is the proportion of people over the age of 55. Here, 290 people over the age of 55, so your N is going to be 290. N1 will be 290. And X1 is going to be the 60 who dreamed in black and white. So X1 will be 60. Now N2 represents it's going to come from the proportion of people under the age of 25. And you're told among 306 people under the age of 25. So N sub 2 will be 306. And then you're told 15 dream in black and white, so X1 is 15. X2 is 15. X2 is 15. Okay, now, this is all we're going to need to use our TI-83 or the TI-84 plus graphing calculator to come up with the Z test statistic. Okay, so in this case here is my graphing calculator. And I'm using a TI-84 plus. The TI-83 works as well with these hypothesis testing. Now to do this, we're going to press the button that says Stat. So here we press the Stat key. We'll use our right arrow key to go to Test. And then we're going to use our down arrow key to find the one that says 2-prop z-test. Here it is right here, 2-prop z-test. And then press enter. Now all you have to enter is X1, N1, X2, and N2. Now we found that X1 was 60. And then N1 was 290. Type in 290 and then enter. X2 was 15, so we type in the 15 and enter. N2 was 306 and then enter. Alright, in this case here, here's P1. Now, you're given 3 choices. Not equal to P2, less than P2, greater than P2. You have to refer to your alternative hypothesis to find out what that is. In your alternative hypothesis, we're told that P1 is greater than P2. So we're going to have to select the one that says greater than P2. So what you want to do is put your blinking cursor on top of greater than P2 and press enter so it can be highlighted. And then use your down arrow key to go down to calculate and then press enter. And as you can see here, this is the output for that. Now if you look at the top, you'll see Z is equal to 5.808340,389. That's going to be your test statistic right there. Now we're going to round that out to 2 decimal places, so that's going to be approximately 5.81. So Z is equal to 5.81. So that's your test statistic. And it's a lot easier to do it that way than doing it the long way that I did using this formula, because I had to find what P1 hat was, what P2 hat was, and then I had to find out what the pooled sample proportion was, and then find out what Q bar was. And then use this formula and substitute those values into that formula to come up with the test statistic of 5.81. Okay. Now step number 6 is calculating the p-value. Now we can get this from the graphing calculator here as well. That lowercase p right here, that's your p-value. But notice this decimal value, 3.1646223, and then e to the negative 9. That's written in scientific notation here. Okay? So if you want to write that in standard form, you have to take this decimal point and move it over 9 places to the left, because this is a negative 9. That's actually 3.16 times 10 to the negative 9th power. So if I was to write that, I would have to write the decimal point with 1, 2, 3, 4, 5, 6, 7, 8 zeros, and then, let's say, 316. So here you can see that p-value is extremely low. Okay, because the p-value represents the probability of getting a test statistic as extreme as the one that we've obtained from the sample data. Here we got a z-value of 5.81, so obviously that p-value is going to be very low, 0.0000316. Now, if you were to use table A-2, you have to draw a normal curve, and the test statistic is this area to the right. Okay, because your alternative hypothesis was greater than, so that means that this is a right tail test. So we're looking for this area to the right. And by looking at table A-2, you'll have to find 5.81, which you're not going to find, because in this case, anything bigger than 3.5, well, from 3.50 and up, you have to use 0.9999, which only represents this area to the left. You want the area to the right, so you have to do 1 minus 0.9999, which will give you 0.0001. Now, if I was to round this to 3 decimal places, then this will be just this, 0.0000. Okay, so that's step number 6. Okay, now step number 7. Is the decision rule. And that's this: if your p-value is less than or equal to alpha, reject the null hypothesis. And our p-value to 3 decimal places is 0.000. Our alpha level was 0.01 from step number 4. And as you can see, that is definitely less than 0.001, because we came up with a very low p-value. Here, if the p-value is low, the null must go. And here, the p-value is very low. So here we're going to reject the null hypothesis. reject the null hypothesis. And then step number 8 is writing our decision rule. I mean, not the decision rule, the conclusion statement. We rejected the null. The claim was the alternative. So that means that there is sufficient evidence to support the claim. So we start by saying that there is sufficient evidence to support the claim that the proportion of people over age 55 who dream in black and white is greater than the proportion for those under 25. Okay. So that 8-step hypothesis testing procedure was actually part A. Okay. Now, part B is that confidence interval. Okay. Because in part B, you're asked to test the claim by constructing an appropriate confidence interval. Here we can use the graphing calculator to do this, but we have to put in the correct confidence level. And I'm going to show you how to find out what the correct confidence level is. Anytime you have a two-tailed test, your confidence level is always going to be equal to 1 minus your alpha level. If you have a one-tailed test, whether it's a left-tailed test or a right-tailed test, then define the confidence level. That's going to be a little bit different. That's going to be 1 minus 2 times your alpha level. Okay? So we go back to our alternative hypothesis. We see that we have a left-tailed test. The alternative hypothesis tells you what type of test you have. You have a right-tailed test. It says greater than. You have a right-tailed test. Okay? It's a right-tailed test. So that means it's a one-tailed test, so our confidence level will be 1 minus 2 times that alpha level. And since that alpha level that we were given is 0.01, that means that the confidence level is 1 minus 2 times 0.01. And in this case, if you do 1 minus 2 times 0.01, you're going to get 0.98. Now, as a percent, that's going to be 98%. So our confidence level is going to be 98%. Okay. All right. Now let's use our graphing calculator to calculate that, to find that confidence interval. Okay, press your stat key. And in this case here, you're going to go over to test, use the right arrow key for test. Now, we're going to use our down arrow key and find the menu item that says 2 prop Z interval. 2 prop Z interval. Once you find that, press enter. It's our data values for x1, x2, n1, and n2 are already given to us because we already did use those values to do our hypothesis testing. So here we got x1 being 60, n1 290, x2 is 15, n2 is 306. But the only thing we need to change is our confidence level, which was 98%. So for C level, we type in 98. And then enter to highlight calculate, and then go ahead and press enter. Now, those decimal values in the parentheses, that represents your confidence interval. That's p hat 1, p hat 2, n1, n2. Now we're going to round those confidence interval limits to 3 decimal places. So my lower limit will be 0.095, my upper limit will be 0.220. Okay, so here's the confidence interval. 0.095 is less than, we have P1 minus P2, and less than 0.220. That's going to be the confidence interval here. So to interpret that, we can say that we are 98% confident that the differences between the proportion of people over 55 who dream in black and white and the proportion for those under 25 fall between 0.095 and 0.220. That's how we interpret that confidence interval. Okay, now part C is an explanation of the results that those over age 55 grew up exposed to media that was displayed in black and white. Well, here's the explanation here that I have. Here, because the confidence interval limits do not include 0, it appears that the proportions are equal. Because the confidence interval limits include any positive values, it appears that the proportion of people over 55 who dream in black and white is greater than the proportion for those under 25. And then that question also asks, can these results be used to verify that explanation? And the answer there will be no. Here the results speak to a possible difference between the proportion of people over 55 and under 25 who dream in black and white, but the results cannot be used to verify the cause of such a difference. Okay. So as you can see here, there are like 3 different parts to that particular example. Okay. All right, now let's look at another example of just this. Okay, and I'm doing example E4. And it says here, rhinoviruses typically cause common colds. Rhinoviruses typically cause common colds. In a test of the effectiveness of Echinacea, 38 of the 43 subjects treated with Echinacea developed rhinovirus infections. In a placebo group, 97 of the 112 subjects developed rhinovirus infections. Use a 0.05 significance level to test the claim that Echinacea has an effect on rhinovirus infections. Complete parts A through C below. Part A, you're going to test the claim using a hypothesis test. Part B, test the claim by constructing an appropriate confidence interval. Test Part C, based on the results, does Echinacea appear to have any effect on the infection rate? Okay. Let's start with Part A. So here, P1 is going to be the Echinacea group. and P2 represents the group that got the placebo. Okay. Alright, step number 1 is writing our original claim in symbolic form. Now, we're already told we want to test the claim that the Echinacea has an effect on rhinovirus infections. Has an effect? Well, we don't know if it's going to be increased or decreased, so we're going to say that there is a difference. So be P1 not equal to P2. And then step number 2 is writing the opposite of the original claim. Well, the opposite of not equal to will be equal to, so the opposite is this: P1 equals P2. And from that we can write our null and alternative hypothesis, which is step number 3. The null has the equal sign, and that's this one right here. P1 equals to P2. Your alternative has the not equal to in it, as P1 is not equal to P2. And by the way, that's your original claim, so I'll write the word claim here. And then step number 4 is to state the significance level. Here the significance level is 0.05. So alpha is equal to 0.05. Alright, now step number 5 is using the graphing calculator to calculate your test statistic. Okay, in this case here, 38 of 43 subjects were treated with Echinacea, and they developed the rhinovirus infection. So here, in this case here, your X1, that's the number of successes, that's 38. N1 is 43, because that's coming from P1, which is your Echinacea group. And then X2 and N2 represent P2, which is your placebo group. And then they tell you 97 of 112 subjects from the placebo group developing rhinovirus infection. So X1 is 97, and X2 is 97, N2 is 112. Okay. So as X2 and N2 are from the placebo group, X1 and N1 represent the Echinacea group. Now let's use our graphing calculator to find out what our test statistic is going to be. Okay, so here's my graphing calculator. Go ahead and press the stack key. And then you're going to go over to test using your right arrow key. The one you're going to select is your 2 prop z-test. So I'm going to use my down arrow key for that. And press enter. Now X1, in this case, is 38, and N1 is 43. So X1, I'll type in 38, then enter. N1 is 43, type in 43 and press enter. X2 is 97, so 97 I'll type in for X2, and then N2 is 112. Okay, now for the P1, you're going to have to choose either not equal to P2, less than P2, or greater than P2. That comes from the alternative hypothesis. Here the alternative hypothesis is P1 is not equal to P2. So we have to select the one that says not equal to P2. So we put the cursor on top of not equal to P2, and then press enter. And then hit your down arrow key to highlight calculate, and then press enter. And as you can see here, this is going to be your test statistic here, where it says Z. Z is equal to, in this case, 0.29346,72575. But to two decimal places, we're going to say 0.29. So your test statistic there will be 0.29. So that's step number 5. Step number 6 is the p-value. Here, that p-value, if you look here, you'll see where lowercase p is. That's your p-value. 0.76916514999. But let's round that off to 3 decimal places, 0.769. So your p-value there will be 0.769. And then step number 7 is your decision rule. If your p-value is less than or equal to alpha, you reject the null. Otherwise, we fail to reject the null hypothesis. So here your p-value there is 0.769. Your alpha level from step number 4 is 0.05. If you compare these two values here, the p-value 0.769 is greater than 0.05. So here we have a high p-value, so the null must fly. So in this case here, we must fail to reject the null hypothesis. So here we're failing to reject the null hypothesis. And then step number 8 is writing the conclusion using simple non-technical terms. Here the claim was the alternative. We failed to reject the null, so we cannot support the claim. So here that there is not sufficient evidence to support the claim. That Echinacea treatment has an effect. Okay, so that's the 8-step hypothesis testing for that particular problem. Okay, and that right there is part A. In part B, they're asking for the confidence interval for this. So part B is the confidence interval. Now we do need to find out what the actual confidence level is going to be. Okay, in this case here, if we look at our alternative hypothesis back in step number 3, we found we have the alternative is P1 is not equal to P2. So here, this is a two-tailed test, by the way. Not equal to means that it's a two-tailed test. So that means the confidence level, I'll just abbreviate CL, is going to be 1 minus whatever the alpha level was. And in this case, your alpha level was 0.05. So it'll be 1 minus 0.05, which will be 0.95. And that's going to be a 95% confidence level. Okay? If you have a one-tailed or a two-tailed test, then your confidence level will be 1 minus 2 times alpha. But for a two-tailed test, it'll be 1 minus the alpha level, because in a two-tailed test, your alpha level is in two tails. Okay. So now let's use our graphing calculator to calculate that, well, to find out what the confidence interval is going to be. Okay, here we press the stat key. Use our right arrow key to highlight test. Use our down arrow key to find the menu item that says 2 prop z interval. 2 prop z interval. Then press enter. Now notice that your data values for x1, n1, x2, and x2 are already given, because we've already did the hypothesis test using those data values. Our confidence level was 95%. So we need to use our down arrow key to change that C level from 98% to 95%. And then hit enter to highlight calculate, and then press enter. And these are your data values here. I mean, this is your confidence interval in the parentheses. Okay? Negative 0.0971, 0.13236. Now we need to round those confidence interval limits to 3 decimal places. So here, we're going to say that the lower limit is negative 0.097. That's going to be less than P1 minus P2 and less than 0.132. And what that's saying is this, that we are 95% confident that the differences in the Echinacea treatment and the placebo treatment is that difference falls between negative 0.097 and 0.132. And as you can see here, in part C, based on the results, does the Echinacea treatment appear to have any effect on the infection rate? And it doesn't. Because as you can see here, the confidence interval limits does include 0. The lower limit is negative, the upper limit is positive. So that means 0 is in between those limits. That tells us that there does not appear to be a significant difference between the two proportions. So there is not sufficient evidence to support the claim that the Echinacea treatment has an effect. So we can say here that the Echinacea treatment does not appear to have a significant effect on the infection rate. Okay, let's do one last example for this video. Okay, let's look at this one right here. In a random sample of males, it was found that 18 write with their left hands and 213 do not. In a random sample of females, it was found that 73 write with their left hands and 434 do not. Use a 0.5 significance level to test the claim that the rate of left-handedness among males is less than that among females. Okay, and then we're going to do part A, test the claim using a hypothesis test. Part B, test the claim by constructing an appropriate confidence interval. And then part C, based on the results, is the rate of left-handedness among males less than the rate of left-handedness among females? Okay, let's start off with part A, doing the hypothesis test. Now I'm going to identify P1 as the left-handed males, and P2 is going to represent the left-handed females. So P1 is your left-handed males, P2 is your left-handed females. Step number 1 is writing the original claim in symbolic form. So in this case here, we're testing the claim that the rate of left-handedness among males is less than that among females. So P sub 1 must be less than P sub 2. So that's the original claim in symbolic notation. Step number 2 is the opposite of the original claim. And in this case, the opposite of less than would be greater than or equal to. So the P1 greater than or equal to P2. And then step number 3, we can write our null and the alternative hypothesis here. The alternative hypothesis always has going to be the statement that does not have equality in it. So it's going to be this one, the original claim. P1 is less than P2. Now I'll write the word claim. So the null must be P1 equals P2, because the null always has the equal sign. The alternative either has less than or greater than or not equal to. Now step number 4 is the level of significance. The alpha level was 0.05. So here alpha is equal to 0.05. And then step number 5, we're going to use the graphing calculator to calculate the test statistic. It's much easier to do it that way than using that other formula. So here, now we have to be careful how we identify what we say x1 is going to be. Well, actually what n1 is going to be. x1 is going to be the 18 that are left-handedness. That's your x1 for males. That's 108. That's 18. But n1 is a little bit different because it says here 18 write with their left hands, 213 do not. And that's for a random sample of males. So we had to add the 18 to the 213, you'll get 231. So that sample N1 for males is 231. Now for females, that's going to be X sub 2. Let's go back up here. 73 write with their left hands, 434 do not. This is your X2 right here, that's 73. But for N2, we have to add the 73 to the 434 that do not write left-handed. And that will give us a total of 507. Okay? So you have to be very careful how you identify N1 and N2. Okay? Because if it says a number does one thing and a second number that does not, you have to add the two together to get the sample size for N1 and N2. Now we can find out what Z is using our calculator. And in this case here, as always, press the stat key. Use your right arrow key to find test. And then we're going to select to prop Z test. And then we're going to enter X1, which is your 18. Enter. N1, that's 231. And then enter. X2 was 73. And N2 was 507. Now we're going to have to look at our alternative hypothesis to find out which one of these we're going to have to select. The alternative has the less than symbol. So we have to select the one that says less than P2. So we use our right arrow key to highlight less than P2. Press enter to highlight it. Use your down arrow key to calculate, to highlight the calculate option, and then hit enter. And there's your test statistic at the top, which is your z. In this case, negative 2.53, rounded to 2 decimal places. So negative 2.53 is going to be your test statistic. Okay, now step number 6 is the p-value, and that's also on the output of your graphing calculator. I'll bring that back up. Here you can see right here, right under the z is your p. That's your p-value. This number right here, rounded to 3 decimal places, we're going to say 0.006. So the p-value there will be 0.006. Now step number 7 is the decision rule, where if the p-value is less than or equal to alpha, you reject the null. Otherwise, you fail to reject the null. So in this case here, that p-value is 0.006. That alpha level from step number 4 was 0.05. And then 0.006, you compare that, you can see that it is less than 0.005. That satisfies the decision rule. So here we're going to reject the null hypothesis. So that's step number 7. Step number 8 is writing the conclusion statement. We rejected the null, and the claim was the alternative hypothesis. So we can say that there is sufficient evidence to support the claim. That the rate of left-handedness among males is less than that among females. Okay. So all of that was part A. So here we found that there was sufficient evidence to support the claim. Now in part B, they want the confidence interval for this. So here part B is going to be the confidence interval. Now in this case, our alpha level was 0.5. The alternative hypothesis had less than. So that tells me right there it is a left tail test. So that means when I find the confidence level, it's going to be 1 minus 2 times the alpha level. Okay? Again, with a one-tail test, it's going to be 1 minus 2 times your alpha level. A two-tail test, your confidence level will be 1 minus that alpha level. So here, that alpha level that was given to us was 0.05. So it'll be 1 minus 2 times 0.05. And 1 minus 2 times 0.05 will be 0.90, which is actually 90%. So our confidence level will be 90%. Now using our graphing calculator, we press the stat key, right arrow to test, go down and find 2 prop z interval, which is this menu item here. Press enter. Notice that your data values for x1, n1, x2, and n2 are already given. Our confidence level is the only thing we need to change, so we use our down arrow key to go down the confidence level, change that to 90%, then hit enter to highlight calculate, and then press enter. And that's your confidence interval, -0.1048 and -0.0273. Okay? So the way we write that confidence interval would be this. There'll be -0.105, -1.05 is less than P1 minus P2 and less than -0.027. And what that means is this, that we are 90% confident that the differences in left-handedness among males and females falls between -0.105 and -0.027. And here, those confidence interval limits are both negative. So that tells us that the true rates of left-handedness are not equal, as indicated here. And there is sufficient evidence to support the claim that the rate of left-handedness among males is less than that among females. Okay. And then part C asks, based on the results, is the rate of left-handedness among males less than the rate of left-handedness among females? And it does appear to be that way. And here the rate of left-handedness among males does appear to be less than the rate of left-handedness among females. Okay. So that would conclude this particular video on doing the hypothesis testing for a claim made about 2 population proportions and constructing a confidence interval estimate of the difference between the 2 population proportions.